Now we review again the definition of a quantum circuit. Typical quantum circuit is composed of a quantum register, quantum gates, and quantum measurements, and also classical register to receive the results of the measurement. This is a visual representation of the quantum circuit. We have here the quantum register. So the quantum register is composed of a group of qubits, and these qubits, we number them like 0, 1, and 2, and so on. And then they could be initialized in 0 state or the ground state or in any combinations of zeros and ones. And then we manipulate the quantum state of this multi-qubit quantum register using quantum gates like H, X, Z, and also multi-qubit gates as well. Once we perform and finish, we have to do the measurement. The measurement will extract the values after we do the computation or we finish running the algorithm of each individual qubit. So I can measure each qubit to be either 0 or 1 if I do my measurement in the computational basis or in the z-axis. And then this number, the 0 and 1, I need to receive it classically. So this is like a transmitted bit now. So I need a classical register to retrieve this classical bit information. And quite often, we need to have a matrix representation of the quantum circuit. The matrix representation, which is a tensor product of all matrices representing quantum gates applied to the qubits. And the whole matrix representation is sort of the net results out of this tensor multiplication of all of these gates. We end up having one complete unitary matrix representing the quantum circuit. So, for example, if we have 2-qubit quantum circuit with X gate applied to the qubit 0, as we see here, and then we have the identity applying to the qubit 1 or nothing applied, so we can put the identity. Both qubits are initialized to 0, then the X will definitely alter the state of the first qubit and invert it to be 1. However, the second one will be left untouched. So the matrix representation of this should reflect this. So if I combine all of these gates in one unitary matrix, I act on the combined Hilbert space of these 2 qubits, then I should get the action of the first qubit inverted. And we can see this here. So the matrix representation of all gates that acts on the quantum register, we can represent it by a U matrix. This acts on the quantum register of Q0 and the Q1. Both of them are initialized to the ground state. So we have U acting on gate 00. Then this U is actually a combination of 2 gates, X gate acting on the first qubit, and the identity acts on the second qubit. Then I can put the 2 matrices, first matrix corresponding to the X gate, second matrix is corresponding to the identity, and then together I get one big matrix, and that will act on my Hilbert space representation of the column vector of the 2 qubits. And then I get the results, which is the first one has been inverted. We see it here. So let's work this numerically. So I have here quantum circuit of Q0, Q1. I have gate X acts on the first, identity acts on the second. So the identity won't do anything. And then my action will be that U, which is composed of X tensor I acting on the 00. That will be like the X acting on the first, identity acting on the second, and then I have 00. And then I can construct the tensor multiplication, which means that I have 0, 1, 1, 0, tensor product 1, 0, 0, 1 acting on 1, 0, 0, 0, because the 2 qubits are initialized in the ground state. So this is a tensor product. How I can perform that? So the tensor product will be that each number of this will be distributed. So I have each number of these one will be multiplied by this full matrix. So I have 0 times 1, 0, 0, 1. Then I have 1 times 1, 0, 0, 1. Then I have 1 times 1, 0, 0, 1. And then I have 0 times 1, 0, 0, 1. This will give me a matrix. It will be 0 for sure. This one, so this number will be multiplied inside, so multiplied by 1, 0, 0, and 1. Then this one will be multiplied inside, so I end up having 1, 0, 0, 1. And then the same here, I have 1, 0, 0, 1, and then I have 0, 0, 0, 0. So you see, this number is multiplied by a matrix, and this one is gone, this one is gone, and then this one is multiplied here, so I end up having this matrix 4 by 4. So this is a unitary circuit representation of the action of 2 gates, X and I, where X acts on the first qubit and I acts on the second qubit. You can have another example. where you reverse. Now we can have another example where we reverse. Now, so we start with identity acts on the first qubit, and then the X gate acts on the second qubit, not the first this time. So similarly, we can work this out. We can have U which acts on Q0 and the Q1. This one is initialized in the ground state. So I can have here 0, 0. Then I have identity O times X acts on 0, 0. Then this would mean that I have 1, 0, 0, 1 tensor 0, 1, 1, 0. And this would mean for us, this acts on 1, 0, 0, 0, the column vector representation of this one. Then I work out the tensor. I have 1 times 0, 0, 1, 0. And I have 0 times 0, 1, 1, 0. And then I have 0 times 0, 1, 1, 0. And then I have 1 times 0, 1, 1, 0. This will give me here 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, then 0, 1, 1, 0. So a minor correction here, so this will be 1. So in that sense, it's clear. We have X gate. Here we have the identity. We can act with this matrix on the quantum register initialized here, and then I can get the result immediately, as we see here. So that one will flip the second, so the second will be 1, which is logical.